All right. Hey, everyone. I'm Sean, and I'm really excited to give you guys all a deep dive into the CS3 hardware architecture. The Cerebras CS3 system, it's our third generation wafer scale system. And it's a generational leap in AI compute because it gives you 2 times higher performance than our previous generation, but at the same power and the same price. Let me show you how we do that. Starting with the foundation, the compute core. And here, we're building on top of the tried and true previous generation WSC2 core that had 48 kilobytes of memory and a 4-way 16-bit data path. On top of that, we are improving performance for AI compute substantially. First, by improving to an 8-way SIMD 16-bit AI compute data path, and also a brand new 16-way SIMD data path for 8-bit AI compute. Now, this is going to accelerate the matrix multiplication of neural networks. But as we all know, neural networks are not just matrix multiplies. So we've also added new instructions to speed up nonlinear functions. And in aggregate, together, we are able to deliver 2 times higher real-world performance per core versus our previous generation. Now, on the memory side, we've improved the local cache to 512 bytes to be able to feed the wider data path and higher performance. Together with the local memory, we're able to get full memory bandwidth for full SIMD performance. Now, that's something that is simply not possible with the GPU memory architecture. So next, what we do is we take this small core and we tile it out 10,000 times into a die. You can think of a die like a traditional chip. Then we tile out 84 of these die across the entire wafer for an aggregate of 900,000 compute cores on a single piece of silicon, a single massive chip. Now, we are uniquely capable of this wafer scale integration because we invented this process in our first generation wafer scale engine. And now we've improved it and we've extended it to the 5-nanometer process in collaboration with TSMC. Now, this is only possible because we've co-designed this from the ground up, from the uniform tile and fabric architecture that allows us to, to fill the entire wafer with the fabric, extending the fabric beyond a single die to a cross die. These are the little blue lines on this diagram. And ultimately, that's what enables the entire wafer to behave like a single massive chip. Now, these little blue lines, they are a big deal. And the reason is when you compare with a traditional chip-to-chip interconnect, for example, how H100 GPUs are interconnected in a DGX server, the difference is just vast. On the wafer, we can connect together 10 times more die, or chips, at 33 times more I/O bandwidth. And all of it is 100 times more power efficient. And I'm not even including the NVLink switches in my calculations here. Now, the reason we can do that is actually pretty simple. And that's because when you compare how you drive bits across between die in the traditional interconnect, you're driving bits through connectors, through printed circuit boards, sometimes even through cables over long distances. That's just significantly harder and more power consumption than on the wafer, where we're driving bits less than a millimeter of distance on silicon. And this is what enables us to treat the entire wafer like a massive chip. So what we did was we take that massive chip and we built a system around it. We call it the CS3 system, and it's purpose-built for wafer scale. Now, when you compare that with GPUs, the performance numbers are just mind-boggling. With this level of performance, we can enable large-scale training on a single chip. For example, you can fine-tune the popular Llama 70 billion parameter model from an open source checkpoint for 1 billion tokens in just a day on a single chip. 70 billion parameter model fine-tuned in a day on a single chip. Now, we didn't stop there. We built a cluster of these CS3s, and we built the entire cluster so that it was designed as a single ML accelerator. Now, the reason we're able to do this is because the WSC3 is big enough to run even the largest models on a single chip. That's what allows us to disaggregate the compute and the memory, and we can train with data parallel only scaling. You can think of this as a cluster-level memory and a cluster-level compute that we've architected specifically so the entire cluster natively behaves like a single device. The way we do that is we put all of the model weights in an external memory called MemoryX. And then we stream these weights into the CS3 system to perform the compute. Now, this is only possible because we have specialized hardware mechanisms in the wafer that trigger the compute as the weights stream in. The weights are never stored on the wafer, not even temporarily, so they never use any of the capacity of the wafer. You can think of this as a specialized memory hierarchy capable of massive models on a single device. Next, we scale this out using a specialized fabric we call SORMX, and it's purpose-built for data parallel only scaling. It has built-in broadcast and reduce mechanisms. And since we're just replicating multi-system scaling, it's the same as running on a single system. It's the same architecture, it's the same execution flow, it's the same software interface. You get scaling to cluster-level compute, but it operates like a single device because it's data parallel only. So in our previous generation cluster, the CS2 cluster, we supported up to 192 CS2 systems in a single cluster. Now that was a lot. But now with the CS3 cluster, we support 2,000 CS3 systems in a single cluster. That's 256 exaflops of FP16 AI compute. And it all programs like a single device. It's beyond supercomputer performance, but single device experience. Now, what enables that is we've significantly upgraded our physical interconnect to be able to scale out. We've upgraded the physical links to 400 gigabits and 800 gigabit links, up from 100 gigabits in the previous generation. And all of this is standards-based Ethernet because it's high performance, it's flexible, it's cost-effective, and doesn't have any of the challenges of custom proprietary interconnects like NVLink or InfiniBand. We also use standards-based RDMA for low overhead and low latency. And when you aggregate all of this together at 2,000 CS3 systems, we have an aggregate cluster bandwidth of 10 petabits per second. It's 10 times more than the previous generation. With that amount of compute, you can train today's state-of-the-art models in just hours or days. For example, the popular Llama 70 billion parameter model that was trained by Meta on a large GPU cluster took about a month to train. With the amount of raw compute in the CS3 cluster, we could train that model in about a day. And what's more, the entire cluster operates like a single device. On the memory side, in our previous generation CS2 cluster, we supported up to 12 terabytes of memory in the MemoryX unit. which supported 240 billion parameter models. Again, that was a lot. But now in the CS3 cluster, we are supporting petabyte-level memory, up to 1.2 petabytes of memory for 24 trillion parameter models, 100 times larger than the previous generation. Now that is only possible because we use hybrid storage for the weight memory. And here, all the weights are stored in DDR5 DRAM and flash memory because it's high performance, it's power, and it's cost effective. In the CS3 cluster, the MemoryX unit can support up to 36 terabytes of DDR5 DRAM, which supports 720 billion parameter models, and up to 1.2 petabytes of flash storage for 24 trillion parameter models. Additionally, the MemoryX unit also has compute to run things like weight optimizer and other miscellaneous functions within the model. And here we've also improved the compute of the MemoryX unit by 2x to keep up and to be able to feed the CS3, which has higher performance. This level of memory is more aggregate memory than some of the biggest GPU or TPU clusters today. And it's all accessible from a single system. With this level of memory, coupled with the compute, we can train tomorrow's trillion parameter models in just days or weeks. Imagine training a 1 trillion parameter llama-style model on thousands of GPUs that would probably take over a year to train. Virtually impossible. On the CS3 cluster, you can train that in 3 weeks. And the whole cluster behaves like a single device. As a user, the entire cluster always looks like a single device, no matter the cluster size, whether it's 1 CS3, 4 CS3s, or 2,000 CS3s. It always looks like a single big device. And your model always fits. Doesn't matter if it's a 1 billion parameter model, 10 billion, 100 billion, trillions of parameters, your model always fits. It always looks like a single big device. And this is a real-world example. This is G42 training their state-of-the-art 30 billion parameter model on the Condor Galaxy 1 cluster. And as you can see, whether they were training on 1 system or 64 systems, it was linear scaling at any scale while operating like a single device. It just worked. There was no complex distribution software, no changes to the parallelism model, no changes to the hyperparameters. It just worked. And we are really proud that this unique capability has been enabled by the wafer scale architecture because it's enabling our users and our customers to train state-of-the-art models every single day. And for me, as a computer architect, this is really exciting because what's enabling all of this is a core design philosophy that we have at Cerebras. And that's to right-size the solution to the problem. Now, some of you may have heard yesterday, our GPU friends, they proudly announced, that they can now connect 2 die together. It's a big deal for them. This is our chip. And in fact, that's our 3rd chip where we can tie 84 die together on a single piece of silicon, a single massive chip. Now, what's really important here is that you can't get there incrementally. You need to take a different approach to be able to get to the scale where the magic happens. You need a certain scale before you can avoid the external chip interconnect that's low performance, high power, uses proprietary chips for switches. 2 die is not going to get you that, not even close. On the wafer, we can run with an on-chip only interconnect and essentially get free high performance communication. You need a certain scale before you can remove and avoid that complexity of distribution software and hybrid model parallelism distribution. On the wafer is big enough to run even the largest models on a single chip so that we can scale with data parallel only scaling and disaggregate memory and compute. When you right-size the solution for the problem, everything just works better. And that's the reason we built a massive chip to solve the massive problems in AI today. But we believe we can and we need to do even better than this. And the reason is simple. Gen AI is exploding at a rate that is unsustainable. If you look at the last 5 years, from BERT to GPT-4, the amount of compute needed to train the state-of-the-art model has increased by 40,000 times in 5 years. 40,000 times more compute to train one model in 5 years. Clearly, this is unsustainable. And so we as a community, we have to find more efficient methods. And at Cerebras, we believe sparsity is the key. Now, why is that? It's because neural networks, they're sparse. There's natural sparsity in neural networks when you use common techniques like ReLU or dropout that introduce a bunch of zeros into the computation. And it turns out that even dense layers of neural networks, they could be made sparse. And that's because models are over-parameterized by design. In fact, you can think of the act of training a neural network model as discovering which of the weights are important and which are not. That's sparsity. So training dense is inherently wasteful and inefficient. But not all hardware can take advantage of all forms of sparsity. And the reason for that is because sparsity acceleration is fundamentally memory bound. All right? And the reason is that dense matrix multiplies, they have a high degree of data reuse, which means you can use techniques like local caching. What this means is you can read a row from the matrix from memory, put it in a local cache, and use it a bunch of times before having to go back out to memory. A dense matrix multiply only requires on the order of 0.001 bytes per physical flop of memory bandwidth. And GPUs, they have that level of memory bandwidth, so they can run dense matrix multiplies. Sparse matrix multiplies, on the other hand, are a completely different story. There's very low data reuse, and so you can't use traditional caching techniques. At the extreme, you have to read each of the rows from the matrix from memory for every sparse element. And therefore, you need order 1,000 times more memory bandwidth per physical flop to be able to run all forms of sparsity. And that level of memory bandwidth is not possible with traditional techniques. Only with the wafer scale engine architecture are we able to get this level of memory bandwidth. And this is the reason why the Cerebras CS-3 is capable of accelerating all forms of sparsity: static or dynamic, structured or unstructured. We can accelerate all forms and translate that into training speed up. Here's some examples. We can accelerate dynamic activation sparsity. Last year, Google published a paper showing that over 95% of the FFN layers in large models can be sparse through ReLU sparsity. That's 1.7 times fewer training flops overall. We can accelerate structure sparsity. As an example, Mistral recently released a mixture of experts model that is running 75% sparse in the FFN layers. That represents about a 2 times reduction in overall training flops. We can also accelerate fully unstructured sparsity, like what we at Cerebras are developing, where we've shown you can induce up to 75% sparsity for up to 2.8 times less training flops. At Cerebras, we believe it's that only through hardware that can accelerate all forms of sparsity, like the ones I mentioned, and even future forms of sparsity that haven't yet been invented by the community, can we really solve the problem of unsustainable training growth. Thank you very much. Now, you might be thinking, sparsity can accelerate training, but can it also help inference? It turns out it can, and in fact, sparsity can enable inference on a variety of hardware, including CPUs. And so, at Cerebras, we've been collaborating with NeuroMagic on doing exactly this. And so next, I'd like to introduce you to Mark Kurtz, who's the CTO of NeuroMagic, who's going to describe the work we've been doing together to enable sparse inference models on CPUs.